Imagine holding the brain of modern civilization between your fingers. That tiny silicon chip inside your phone or laptop contains billions of circuits, etched with astonishing precision. But how do we actually print these microscopic highways of electricity? Welcome to the world of photolithography, the process that makes the digital age possible. Let's start with the big picture. Photolithography is like high-tech photography, but instead of capturing an image on film, we're projecting patterns onto silicon wafers to define where transistors and wires will live. Think of it as the ultimate light-powered stencil. First, we need a canvas, a wafer of pure silicon, polished until it's mirror smooth. This wafer is coated with a special light-sensitive chemical called photoresist. If you've ever used sunscreen, you already get the idea. Photoresist reacts to light, but instead of protecting skin, it decides which parts of the wafer will be etched and which parts will stay safe. Now comes the magic. Engineers use a mask, a plate with intricate patterns representing the circuit design. When ultraviolet light shines through the mask, it projects the design onto the wafer. The exposed photoresist changes its chemical structure, becoming either soluble or insoluble depending on the type used. This is where the photo in photolithography earns its name. After exposure, the wafer takes a chemical bath. The soluble photoresist washes away, leaving behind a crisp pattern that matches the mask. Imagine peeling away parts of a stencil to reveal the design underneath. What's left is a roadmap for where material will be added or removed next. We etch. Using plasma or chemicals, the wafer's exposed silicon is carved away, creating trenches or openings. Alternatively, new materials like metals or insulators can be deposited only in the patterned regions. Layer by layer, this builds the complex architecture of a chip: transistors, interconnects, and insulating barriers stacked like a microscopic skyscraper. But here's the kicker. The scale. Modern photolithography can define features smaller than 10 nanometers. To put that in perspective, a human hair is about 80,000 nanometers wide. We're talking about structures so small that quantum effects start to matter. Achieving this requires extreme ultraviolet light EUV wavelengths, so short they border on X-rays. Generating EUV is a feat in itself, involving plasma bursts hotter than the surface of the sun. And it doesn't stop at one layer. A single chip might require dozens of photolithography steps, each with a different mask, each aligned with atomic precision. If the layers don't line up, the chip fails. That's why chip fabs are some of the most advanced facilities on Earth, with clean rooms cleaner than surgical theaters and machines costing hundreds of millions of dollars. So why go through all this trouble? Because photolithography is the only way we can mass-produce chips with billions of transistors. It's the secret behind Moore's law, the relentless shrinking of circuits that has powered faster computers, smarter phones, and breakthroughs in AI, medicine, and space exploration. Think about it. Every time you swipe on your phone, stream a video, or run a simulation, you're relying on patterns of light projected onto silicon. Photolithography is the invisible printing press of the digital age, turning beams of light into the engines of progress. And here's the hook: this process isn't just about making chips smaller, it's about redefining what's possible. As engineers push photolithography to its limits, they're opening doors to quantum computing, neuromorphic processors, and technologies we can barely imagine today. The future of innovation is literally written in light. So the next time you hold a device, remember, inside, there's a masterpiece of engineering, etched by photons, sculpted by chemistry, and assembled with precision beyond human hands. That's photolithography, the art of printing the future.